We'd proceed in flux calculation, divergence calculation, and then post that we will see curl fundamentals in flux. Okay, so what we have seen till now as far as calculation of flux is concerned. So flux is something that is surface integral. Calculus integration. Calculus Calculus integration means multiplication. If it is not numeric, if multiplication is not numeric, then it is calculus. Not numeric means it is algebraic. So algebraic multiplication if we take, then multiplication means two items. How we multiply two items when we are trying to calculate area of a rectangle. This side, this side, if we multiply, we get the area of a rectangle. So that approach integral calculus takes, and when there is multiplication comes, it considers that it is two sides of a rectangle, and then it tries to calculate the area. This is this is something called integral calculus. Like if I have one side as x and other side as 2, then multiplication is 2 into x. That is nothing but area of a rectangle also. Or in terms of calculus, it is 2 dx. 2 into x. Now it consider one is independent component, one is dependent component. So 2 into x, x is along x-axis, then it consider x as the independent component and 2 as dependent component. Fx, function over x, that is 2. So for that the calculation of the multiplication in terms of integration calculus is fx dx. D comes into the picture. Otherwise 2 into x get converted into 2 dx. 2 is fx. So fx dx. It makes sense, right? If I am calculating area of a rectangle and height is 2 and width is x, 2 into x. What about height is again variable? That is x. Height is x. Whereas width is x. Width is x makes sense. It is independent component. But if dependent component is x, which is varying upon the as per the x I take, then it is not rectangle. It is triangle. Directly x into x would not work because area of a triangle is x square by 2. So x into 2 into x is the net area of the rectangle. True. If height is 2, but if its height is x, then x into x will not work. X dx will work. 2 into 2 dx will work. X dx will work. So here it is integral calculus. What we are trying to do? We are trying to, if I have a fx, it's line integral along x-axis. If I have a fx, then it's line integral along the x-axis. What about if I have fx and its surface integral along xy plane? What about its surface integral along any plane? What about the line integral not along x-axis, line integral along any line? What about differentiation of algebraic function along any vector, not along the x-axis? So many things comes into the picture. So surface integral of an algebra, surface integral of an algebra or of an algebra along any surface. If it is x-axis and y-axis plane, then we can say that the algebra, whatever we have, dx, dy, the area, integration along area, not integration along x-axis or y-axis or whatever. Integration along xy plane. If that is the case, and I have equation as fxy dx dy or dA. This is surface integral of fxy along surface xy plane about any a, dA about any a. Now, if we have the algebra function in terms of a vector, then if it is then it is called vector field. Algebraic vector is called vector field. If it is capital F equal to x plus yi plus x plus sine yj. Now each component is algebra, and then we want to calculate surface integral along a particular surface. But integration would work only on algebra, not on vector. Then that surface we try to find its direction, and then dot product capital F, capital F, capital F dot dA vector, capital F dot dA vector. So that is considered dA vector. So that is considered as surface integral. I'm not talking about xy plane. dA, dA, A can be anything. XY plane, XZ plane, YZ plane, or any plane. Any plane. Oops, sorry. It can be any curved region also. So this is plane, this is plane. This is also a surface, right? Then along any surface. Now surface, if it is like this, then it turns up into a vector field. Capital F dot dA vector. This is full form of the surface integral, like the full form of 2 into x multiplication is fx dx, 2 dx. This is full form of any multiplication. Now 2 you can take x, sin x, log x, dx. That way, better full form of this is that if you say fx rather than fx, you call it a vector field, where vector field has fx, gx, and those as component, even higher. Numeric to algebra, algebra to vector, where vector has algebra as its component, and then dot dx, dx vector, dr vector. Now integration of a vector field along a particular direction, particular vector. Integration of a vector field along particular area. Capital F vector field, capital F vector dot product of vector, small d a vector. Now this is the pioneer, not this. We will move later into Jacobian. It is even higher. So this is what is the surface integral of a algebraic vector. Capital F vector dot dA vector, integration over the surface. Now if I have a surface, dA vector, area vector, everywhere area vector is different. If this is the surface, slant surface, then this is the area vector perpendicular to the surface. But if this is the surface, then area vector everywhere it is different. If it is different, then it is algebraic. Then A vector is a vector field. So A vector is a vector field. Now we did many things. So when we do surface integral, we call it as flux calculation. Flux calculation, like if I have a velocity, if I have a liquid which has a velocity and it hits a surface, then how much is the liquid that is coming out of the surface? Volume per second. That is the flux. If the surface is closed one and then there is a vector field, then how much is the volume that is coming out of the closed one divided by the volume is divergence. Divergence of a vector field, it shows its nature to diverge or converge. So diverge means if divergence, that is surface integral along a closed surface divided by volume is the divergence. If it is positive, then it radiates. If it is negative, if it is positive, then it radiates. But if it is negative, then it converts, it absorbs. If it is zero, then inside that volume do not behave like a energy point. Energy is coming from outside, energy is coming from outside and it is passing through. If that is the case, then flux is 0 of a closed region. So this happens typically when vector field is numeric 2i plus 3j plus 4k. If that is the case, then if I have a surface, if I have a surface like this and vector field that is passing is a static vector, then if I divide into half, if I draw a line and right side is one half and left side is another half, then left side whatever flux is calculated, right side would nullify it. So it becomes 0. So left side, the area vector is negative of x-axis. If this is x-axis, this is y-axis, this is z-axis, then it would nullify the area. This is the area vector, then this side area vector is like this. If this side area vector is up, then this side area vector is down. So it will go. But if the vector field is algebraic equation, not a static vector, then there is a high chance that this volume would behave like a radiation of vector field. Means divergence is positive. Like we saw that if I have a vector field xi plus yj plus zk or r vector, if that is the vector field, then if I try to calculate the divergence at any volume, then it has some value. What is the calculation for the divergence? You take any volume, calculate the surface integral, divide it by volume. Volume tends to 0. It should behave like a point. Then from point, what is the divergence of the energy that you can see? So for the vector field, one way, there are two ways to calculate the divergence. One way is geometric way, other way is algebraic way. Geometric way is you calculate the surface integral flux, divide it by the volume. That is the divergence calculation. Other is algebraic way. If capital F is vector field, then capital F1, F2, F3 are its component, then capital F equal to F1i plus F2j plus F3k. If that is the case, then divergence of xi plus yj plus zk is dx by dx plus dyy by dy plus dz by dz. Then it will result into 3. So there is divergence. So divergence, if it results into a numeric value like 3, then it is position independent. If you are calculating the divergence through geometric way and you take a sphere, you keep the sphere centered at the origin or you keep the sphere centered at 200. This is what example we took. Divergence will be same because it is not position independent. Divergence coming as 3 through algebraic way. But it is always shape independent. If you have a vector field, the net divergence is df1 by dx plus df2 by dy plus df3 by dz, then there is nothing called shape comes into the picture. It is shape independent. If this value is static, not algebraic function, like vector field is x square plus y square I plus y square plus z square j plus z square plus x square k. What is the divergence? Then it is 2x plus 2y plus 2z. Divergence itself is coming as algebraic equation. Now you have to calculate divergence at a particular point because x, y, z would change. If it doesn't change, then it is position independent, shape independent. It is always shape independent. Either divergence come as algebraic or it does not come as algebraic. We took example of R vector as the vector field xi plus yj plus zk. And then when I took a cube that is centered at the origin, a sphere centered at the origin, and we saw through geometric way calculating the flux by the volume, it comes as 3 1 both cases. Now I shifted the sphere centered at 200. X is 2, y is 0, z is 0. It is kept on x-axis. Now try to calculate the divergence. So we will try again. Last video we tried and there was some confusion in the kind of it's because if I take Cartesian coordinate, then we calculate upper half of the sphere. So upper half, then we multiply it by 2. We'll try it again. If I have a sphere, it is centered at 2, 0, 0. Then what is the divergence? What is the flux? Where the vector field is xi plus yj plus zk. The flux is capital F vector field dot dA vector. dA vector, dA area vector in Cartesian coordinate is minus dz by dxi minus dz by dyj plus k vector, and then xy and xy plane. D area means xy plane. dx dy. Now here I have a sphere centered at origin. Then equation of a sphere is x minus centered at 2, 2, 0, 0. Then it is x minus 2 whole square plus y minus 0 whole square plus z minus 0 whole square equal to a square. A small a. A is the radius of the sphere. Then z equal to square root of a square minus x minus 2 whole square minus y square. It's a square root. That is z. Now minus dz by dx. So minus dz by dx would appear as x minus minus dz by dx. X minus 2 divided by square root of a square minus y square minus x minus 2 whole square minus dz by dy minus dz by dy would result in y divided by square root of a square minus y square x minus 2 whole square plus k vector dot product with xi plus yj plus zk. That would result in x into x minus 2 divided by square root of a square minus y square minus x minus 2 whole square plus y square divided by x square square root of a square minus y square minus x minus 2 whole square plus z. So z is the square root of a square minus y square minus x minus 2 whole square. If I settle it down, then it becomes x into x minus 2 plus y square plus a square minus y square minus x minus 2 whole square divided by square root of a square minus y square minus x minus a whole square. Okay, and then dx dy minus y square gone, and now we have x minus x into x minus a plus a square minus x minus 2 whole square. Now x into x minus 2 I can write it as x minus 2 plus 2 and then x minus 2. X can be written as x minus 2 plus 2. So it will become x minus 2 whole square plus 2x minus 2 plus a square minus x minus 2 whole square. X minus 2 whole square gone. Now it is 2x minus 2 plus a square divided by square root of a square minus y square minus x minus a whole square dx dy. Now consider integration of x is 2 minus a to 2 plus a. Y is minus a to a. Now this is pure flux calculation surface integral. Now consider x minus 2 equal to square root of a square minus y square, that is the radius, cos theta. This is polar coordinate. Then dx equal to square root of a square minus y square minus sine theta d theta. Now we will replace with dx. Now we have 2 into x minus 2 plus a square divided by square root of a square minus y square minus x minus 2 whole square dx dy. Dx will come at the square root of a square minus y square minus sine theta d theta. Now here at the denominator I can take out a square minus y square, and again it will be square root of 1 minus cos square theta. At the end denominator will be settled in the square root of a square minus y square sine theta. There minus sine theta and a square root of a square minus y square, everything will cut down. Minus would remain. So minus I can keep outside, and here it is 2x minus 2 plus a square d theta. Now if I integrate with d theta, then it will, now x minus 2, 2x minus 2. X minus 2 I would replace with the square root of a square minus y square cos theta. Now I have 2 square root of a square minus y square cos theta plus a square d theta. Now integrate with the d theta, it will come as a as 2 square root of a square minus y square cos theta integration is minus sin theta plus a square theta. Now integration, now if I take the sphere, if this is a sphere and this is x-axis, then left is a 2 minus a, right is 2 plus a, because it is centered at 2 0 0. But if I talk in polar coordinate, the left side will be pi angle and right side will be 0, pi to 0. That is the integration of the theta, pi to 0. Now here it is 2 square root of a square minus y square minus sin theta. Pi to 0 means full 0. And here a square theta, pi to 0 means minus a square pi. Minus I had kept outside, minus minus gone, a square pi. A square pi. Now dy is minus a to a, 2a. So it becomes 2a to the power 3 pi. 2 pi a to the power 3 is the top hemisphere flux calculation. I multiplied by 2. I'll get the bottom hemisphere also. So 4 pi a to the power 3 is the net flux of a sphere as far as vector field is xi plus yj plus zk divided by the volume of the sphere, that is 4 pi a to the power by 3. So 4 pi a to the power 3 divided by 4 pi a to the power 3 by 3, 3. So divergence is 3. Now you take this sphere any place, 2, 2, 2, 2, 2, 0, 0, 2, 2, anywhere. Now use this fundamental, it can be taken as an assignment, and now shift the sphere at 2, 2, 0. Instead of 2, 0, 0, shift the sphere at 2, 2, 0. Shift the sphere at 2, 2, 2. Now try to calculate the surface integral divided by the volume, the divergence. So this is the kind of concept for the divergence being shape independent, and if divergence is coming as a numeric value, then it is position independent also. What is remaining in divergence calculation? We have seen many things. Like if I have to calculate divergence of a equation where it is in form of algebraic equation multiplied by a vector, like r vector divided by magnitude of r vector to the power 3. That is the case, then it is xi plus yj plus zk divided by x square plus y square plus z square to the power 3 by 2. Then there are two things. One is 1 by x square plus y square plus z square to the power 3 by 2 multiplied by a vector, that is xi plus yj plus zk. So left side I can say it is G, that is algebraic equation. Right side I can say it is capital F vector, that is a vector field. If that is the case, the net divergence is vector field capital F dot divergence dot gradient field of G plus G into divergence of F. This is also we saw to things to make life simple. What is the biggest thing now? If I have a divergence, then I can calculate the surface integral back. That is flux back. That is divergence of vector field F dV. Flux divided by dV equal to divergence. dV, you take this side, divergence integration with dV along the volume is the flux back. Like if I have x square plus y square plus z, x square plus y square I plus x square y square plus z square j plus z square plus k square k. If this is the vector field, what is the divergence through algebraic way? df1 by dx plus df2 by dy plus df3 by dz. Then it will come as 2x plus 2y plus 2z. Now do the integration with the volume, you will get the flux back. Like if you want to flux through any cube which has unit length, unit width and unit height, then 2x plus 2y plus 2z and then dv, that is dx, dy, dz. Now integrate over the volume. If you integrate over the volume, then x would be minus 1 minus half to half, y would be minus half to half, and z would be minus half to half. And this 2x, 2y, 2z, first integration with dx would resolve into 2x square by 2 plus yx plus zx. Now settle x with minus half to half and see what is the result. It will come in y and z. Again integrate with y, settle with minus half to half. Again integrate with z, settle with minus half to half. You will get the flux. No need to calculate flux side by side. What? Same way, someone can try with the sphere also. What is the other thing that we saw? What is no one thought that if the flux calculation is capital F dot dA vector, capital F dot dA vector, integration over surface, capital F can be a curl vector. Curl vector means capital F vector field equal to curl of G vector, capital G, capital F. There is another vector in the world. If you calculate the curl, that is dg2 by dy minus dg1 by dx, that is the calculation of curl through geometric way. dg2 by dy minus dg1 by dx and then k vector. This is cross product. Or if you have three-dimensional, then you can go along like this, like dg3 by dy minus dg2 by dz I vector plus d d plus dg2 by dx minus dg1 by dy k vector plus, I mean that was minus because this is a cross product we are taking trigonometry, plus dg plus dg2 by dy minus dg1 by dx k. So the curl vector, if vector field F for which we are calculating the flux, it happens to be a curl vector G, so that curl of G equal to F, a new vector arrives into the picture G, then divergence of curl of G, divergence of F, in that fashion it is guaranteed it is 0. So divergence of curl of G is 0, or divergence of F, in that sense it is 0. How it is? If a vector field is resultant of curl of G and curl of G is non-zero, this proves that curl of G means tendency to make something rotate. If dg2 by dy minus dg1 by dx is non-zero and it results in vector field F, then df1 by dx plus df2 by dy will be 0. If any vector field is producing curling, then the divergence of that vector field will be 0. How it is possible? It is possible. How it is possible? Okay, so it is something like, if I have a surface, consider this is a surface. Oops, this is a surface. This is empty, and this is a surface. Okay, now if I am calculating the, what is the Stokes theorem? If I have a curl vector, if I have a vector field G, if I have a vector field G, capital G dot dr vector, line integral of capital G along a boundary of a, consider if I close this and take it out, then this is the flat region that is closing this surface. This flat region has a boundary. This flat region has a boundary. Now, if I calculate the line integral of any vector field capital G along this boundary, is nothing but capital G dot dr vector integral along this boundary, that is equivalent to curl of G, and that is integral over the This boundary, closed boundary, is making a surface. This is what the Stokes theorem. Okay. Now consider I have a, now if I calculating the divergence, I will take now a closed region, closed surface. This is fully closed now. I closed it. Now if I close it, now consider I draw a line like this. I draw a line like this. Now this is a boundary. Left side there is a surface, right side there is a surface. Now if I take the surface integral here, cap curl of G dA, curl of G dA, that equivalent to line integral of G along the boundary. So if I try to calculate the surface integral of left side of curl of G, that is G is line integral here. If I calculate line integral, very nice. Now right side if I take, then again since they share the same boundary, again I have to calculate the line integral. Okay, if I calculate line integral, but direction would be opposite because they are sharing the same surface. So one side line integral will be counterclockwise, one will be clockwise. Net addition, because since I am calculating full flux of the closed region where the vector field F is curl vector G, then it will be 0. This side surface and then line integral, this side surface and then line integral opposite will tend to 0. If that is the case, then if my vector field happens to be a curl vector, it has a vector field capital F can be represented as curl of G vector, then divergence of this this vector field F will be 0. Divergence of curl of G will be 0 or divergence of F will be 0, but not necessary that every vector field F can be represented as curl of any other vector. Go in the world and try to search any vector field for which curl dg2 by dy minus dg1 by dx would result back in F1. If that is the case, then F result in F, then F would divergence of F would be 0. That is another theorem. What we had seen in the curl fundament, if curl is 0, dg2 by dy minus dg1 by dx is 0, then the G is considered as path independent. If you remember, path independent means G can be represented as a gradient vector of a potential function for which a potential function would exist and for which gradient vector would be capital F. So from there you can start, then for curl, and then here flux and divergence all are interrelated. So this is all about the flux calculation. Mind blowing, very nice. So we will proceed in the parametric surface calculation, parametric vector, anyway I have seen parameterization of an algebra. If I have algebraic line that is y equal to square root of a square minus x square, that is a line that is parameter of a circle. Now there are two things, y and x. Can I bring x and y as a function of another only one independent component? This is called parametric function. y equal to a sine t, x equal to a sine a cos t. Now here variable is t only, a is constant. So only one factor comes into the picture. Now I can represent same thing as a vector. Now vector, position vector a cos ti plus a sin tj is representation of a circle where independent component is t only. So x part is variable of t and y part is variable of t only. So x equal to ft, y equal to gt. So if I have a surface equation, line equation, if the variable what we see x, y, z, if I represent it as a parametric function, Parametric means a function which takes a parameter like ft function over t. If, if that is the case, then it is called vectorization or parameterization of an algebraic equation as a vector. What about parametric surface? Surface vector parameterization. So that there we will proceed. I thought of starting Jacobian, but it will be too much. So that now we did vector integration along a surface, any surface, that is the most advanced one. We will see surface vector integration along any surface. So right now we have line vector integration along any surface vector integration along any surface, that we will see in Jacobian. But first we will see how I can turn a surface algebraic equation into a vector equation through parameterization. So there we would proceed.